So guys, today we will continue chapter 4. We will not have class next Wednesday. Instead, we will make up for that class on Friday.
Professor, do you mean this coming Wednesday or the?
I mean this coming Wednesday. So on Friday, which is
What if you can't make it on Friday?
Yeah, I have another class from 2:30 to 3:45.
Can we make me too? Can we make it later in the day?
I can make it later in the day, but the thing is, I
during the day.
record these classes, but I can. So guys, would it be okay if I have the class on Friday but later?
Yeah. You could
Yeah,
also
If we
re-record.
just watch the recording,
watch-
if we can't
yeah.
make it.
Yeah, that's an option, but I want you to be in class too.
4 to 5 works.
I don't know,
In the
but
morning,
like I guess.
4 to 5 is okay.
Let me say 4 to Friday 4 p.m. to 5:15 p.m. Okay.
Those who can't join, we can still watch the recording, right?
You can watch the recording, but I still want, I mean, if you can, I want you to have in class. Okay, so that Friday is October
9th.
Yes, October 9th.
Are all classes canceled on Wednesday? Do you guys know?
No, guys, I have some.
Oh, okay.
My
So,
Wednesday is really busy, so that's why.
Personal stuff.
oh, okay.
Do we
okay.
have class on Monday?
No, I think we don't. I guess.
No,
We have
Monday
Wednesday.
we don't have class, but I don't know why it says Wednesday follow a Monday schedule. I don't understand what's that point.
Okay, so
okay, so
if Wednesday follows Monday, then that's a CUNY's thing. So we cannot really. How do I mute everybody? I mean, if the calendar says the Wednesday follows Monday, then that's how it is. Or I will check it. If Wednesday follows Monday, then it means probably that we will have 2 classes. I don't know. I have to check it. So. Yeah. But our next class is on Friday, and I do record classes. So, but the next class will be entirely on. Okay, let me write it down. The next class, which is on Friday, October 9th, from 4 p.m. to 5:15 p.m., will be entirely about R. Okay, so I want you to download R and install it in your computers. I'm not sure if I uploaded the instructions, if I gave you the instructions for this. I haven't, I think. I haven't, I said I haven't, but I will post the announcement about how to download R. So, assignment. To me is post the details how to download and install R and RStudio on your computers.
Professor, sorry to interrupt, but you did put an announcement regarding that.
I did announce it.
Yeah.
Really? Oh, let me see.
You announced it on the first day, I believe.
Oh, really?
Yeah.
Oh, okay. So that's already there. Sorry, guys. I see. I was looking at the announcement, but I have it on the course documents. So that means that I already have done this assignment even before I okay, guys, but you get the idea, right? So then your assignment will be to download R and RStudio on your computers. Download and install those. The instructions are on the CUNY Blackboard in the course documents section. Am I clear?
Yes.
And so the next class will be, as I said, which is not on Wednesday, but on Friday instead, Friday, October 9th, from 4 to 5:15 p.m. The next class will be entirely about R, how to use R, and some good features of R. Okay, so if this is clear, then let me continue and hopefully finish chapter 4. Okay, so this chapter was about what? Was about estimating the effect of an independent variable on the dependent variable. And we had a few expressions that I wanted you guys to remember, first to understand, and then we remember. So let me remind you those. First, we have, I call these population. How many students do I have? Population line. Sorry, not population line, but I call these population relationship. And that was what? Yi equals beta 0 plus beta 1 times xi plus ui. What is ui? Can you tell me?
The error between the certain line and the actual result.
That's very cool.
The sample line or the
No. You said it right before. Not the sample line.
I don't know which line, but
the population line. And the actual y. So ui, which is known as the error, or in other words, this is another name of that disturbance, is what? Ui equals, and now you can tell me, right? The actual yi minus what? Expected yi, conditional on your x. That's the disturbance term. So guys, you need to understand every single term that I'm talking about. And then you can consider that you understand this stuff. But you will understand this over time. Don't worry about that. Now let's make an assumption. Let's assume, and we will talk about the assumptions later. Let's assume that expectation of ui conditional on xi equals 0. Okay. Then we can get the population line simply by taking expectation on both sides of this equation. Let's take the expectation of both sides of that equation. That will be what? Expectation of yi equals expectation of that entire thing, which is beta 0 plus beta 1 times xi plus ui. But then this equals expectation of yi equals expectation of beta 0 plus, expectation of beta 1 times xi plus expectation, okay, have to be, so if you apply the law of iterated expectations, then you would be getting what I have here. But even if you don't want to apply the law of iterated expectations, then you can write this. Conditional on xi equals expectation of beta 0 conditional on xi plus expectation of beta 1 times xi conditional on xi plus expectation of ui conditional on xi. And this is 0, right? Why? Guys, I need you to get involved.
You said it was 0.
Because that's by assumption, right? And this assumption is one of the key ordinary least squares assumptions. One of the key assumptions, right? This will be what? Beta 0, right? And this will be what? Beta 1 times xi. Why? Because beta 0 is a constant. Simply we don't know the value of that. That's the true value, that's the true population parameter that we don't know. But there is the value that we don't know. The value is there, simply we don't know. And it's constant. And simply because of that, the expectation of beta 0 conditional on xi will be beta 0. Here condition is xi. So that's why you have beta 1 times xi. So then you can rewrite this expression like this. Expectation of yi conditional on xi equals beta 0 plus beta 1 times xi. And what do we call this? We call this population line. Okay. Now, that's the population line, but
Perfect.
yes.
I have a question. So can you just go a little bit up when you wrote expectation? It's P0, B0. You stated that the so for the first part of the right hand side equation, the expectation of P0 conditional xi is constant itself.
Yeah, because why? Because beta 0 is a constant. We don't know the value of beta 0, but we know that it is constant.
And the expectation of constant is constant, right?
Is constant, right?
Okay.
Right.
Okay. Thank you.
That would imply beta 1 is not a constant, right?
No. Both guys, beta 0 and beta 1 are unknown constants.
Okay, thank you.
And we are after finding these constants, but we will never be able to do that. But we will be able to find the estimates of these constants. And we call those estimates beta 0 hat and beta 1 hat. Am I clear? Now, there's another expression that we call the sample line. And the expression for the sample line is this: y hat I equals beta 0 hat plus beta 1 hat times xi. This is the sample line. Why is the sample line different from the population line?
Because it's estimated.
Yeah, but if you look at these two expressions, what is the only difference on the right-hand side? What are the differences?
We use sample beta 0 and beta 1 instead of
Yes,
actual.
very true. It's very true. So, so how are we finding beta 0 hat and beta 1 hat? We use a method that is known as the ordinary least squares, or OLS estimation method, to find beta 0 hat and beta 1 hat. Do you guys remember what does the OLS do?
Can I take a wild guess?
Sure, sure.
I think it might be the deviation of the sample mean of the dot from the line, the sample line squared, maybe.
Does it minimize the sum of the squared residuals?
Very true. So the first one was somewhat right, but not entirely. The second one was completely correct. So the OLS minimizes the sum of squared residuals but okay, so did we define residuals? We didn't, right? So residual is u hat I, which equals what? Can you tell me? That will be yi minus
Expectation of
no yi hat. That's the residual. But then you got confused because if you subtract expectation of yi conditional on xi from yi, then you get the error. That's the true error, which we never observe, but we observe residual, which is yi minus yi hat. So the OLS minimizes the sum of squared residuals with respect to what?
Sample line.
Can you be more precise? You're right, but can you be?
You mean the equation of the line?
I mean, you are minimizing with respect to some stuff. You're minimizing with respect to beta 0 hat and beta 1 hat, right? So the problem can be written like this: minimize with respect to beta 0 hat and beta 1 hat, what? The sum for what? Squared residuals, where I changes from 1 to n, and n is your sample size. But then we know that u hat I already wrote that up is what? Is yi minus yi hat squared. But again, what is yi hat? Sum I changes from 1 to n, and then yi minus And then yi hat we know is beta 0 hat plus beta 1 hat times xi. And you are doing this. In the class slides, if a very simplified version, you're saying that n equals 2. And this minimization problem is solved for z. N is never 2, right? And should be greater than, much more greater than 2. But for the illustration, it is solved for when n equals 2. This minimization problem is solved for n equals 2. And the derivations are in the class. Like if you're interested, you can take a look at it. It's on page.
I have a question, Professor.
Yeah, sure.
So we use this equation of minimizing equation to find the B0 and B1, right?
Yeah, I would say, okay, so you are finding what? Beta 0 hat and beta 1 hat.
Mm-hmm. But
yeah, in the class slides, you have B0 and B1. There is another notation for beta hat 1 and beta 0 hat. So we have some notations, guys. So the true ones will always be denoted by beta 0, beta 1. These are true. Population parameters. But then you have sample estimates that are either denoted by beta 0 or B0 or beta 1 hat or B1. So these are just notations, right? So if you do that minimization, you get what? That beta 0 hat equals, okay, first you are obtaining beta 1 hat, which is s of xy divided by s squared of xy. S of xy is just simple covariance between x and y, and sorry, in the numerator I should have s squared of x. And beta 0 hat is y bar minus beta 1 hat times x bar. And then you want to see what's this s of xy and the squared of s squared of x, right? So this equals the sum of xi minus x bar times yi minus y bar. I changes from 1 to the sample size, and sample size is n, and in the denominator you have the variance of x, which is xi minus x bar square. I changes from 1 to the sample size n, right? And that's how you find it. So can you find it in Excel? So in Excel, you have data on X, and let's say you have data on X and data on Y. Let's say in Excel you have Y and you have X, right? And you have data on those, Y and X, right? So this is, let's say, N, 1, 2, 3, 4, 5. And I can write here, let's say 6, 17, 2, 3, 0.6, 3, 4, 15, let's say 176, 2, whatever. If I give you this is your data, right? Let's say. Will you be able to find beta hat 1? In Excel, you will be, right? You can calculate the x bar, you can calculate y bar from this x, and then you can calculate this numerator and then calculate the denominator, and you are able to find, given this data set, you're able to find beta hat 1. Am I clear?
A question, Professor.
Sure.
So when you mean x bar, what do you mean by x bar?
That's average, that's mean of x.
Okay. And
That's
when you mean
when I say x bar, that's the sample mean of x. This is the sample data, right?
okay. So okay.
But also you have expectation of x, but that you never know because you don't have access to all the population, all the observations in the population. So then this is your best. Guys, am I clear? Then beta 0 hat, can you calculate it based on this data?
Yep.
Yeah, because beta 1 hat is already calculated in the first stage here, and then you have x bar and y bar, right? You can calculate beta 0 hat. And those are when you calculate, once you calculate, you get the numbers, then they will be the estimates. Beta 0 hat and beta 1 hat are estimators of what?
The population.
Very true. But once you calculate beta 0 hat and beta 1 hat, based on the expressions that I gave you here, you get the estimates. Okay?
Professor, can you scroll up? I have a question.
Yeah. You get the estimates of what? Guys, I need you to get involved.
the beta 0 and beta 1?
Is it the population line?
Yeah, because population lies is entirely determined by these two parameters. So, okay, very good. So we are doing fine. Now let me talk about the fit, right?
Question, Professor.
Sure.
What do you mean by beta 0 and beta 1? Are there points on the graph?
No. Let me now remind you this. So we have, let's say, these points, right?
Mm-hmm.
And let's say these are white points, let's say, are sample points. But also we have population, right? Which clearly have more points, right?
Mm-hmm.
So the population in this example consists of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So capital N equals 10, right?
Okay.
But small n equals what?
6.
Very good. Okay, so these are just points. And you know that there is a line which is the best fit, right? And let's say this is the line. That's the best fit. And that line is the population line, which is what? The expectation of yi conditional on xi. but then you know this is what? Beta 0 plus beta 1 times xi. But here you made the assumption that what? It's 0.
Quick question, Professor. Sorry to interrupt.
No, that's fine.
Does the when you state expectation of y is conditional xi, you stated is equals to b0 plus b1 x1. Does that mean that b0 is a point on y-axis?
No. First, please say beta 0, beta 1, because b0 is this, which is like another notation for the estimate.
Okay.
So please say beta 0.
Isn't the beta 0 plus beta 1 dot xi represent y is equals to mx plus
Yeah,
c
so now I am returning this question to you. Then you have this line. On this line, where do you have beta 0? This line is given, the formal expression of that line is this. Where is beta 0? What is beta 0? Beta 0 is the intercept, right?
Mm-hmm.
So that will be this.
Okay.
What is beta 1?
Slope.
Beta 1 is the slope, yes, of this line.
Got it.
Do you see what I mean? So, okay, so line, straight line is completely determined by two parameters, the slope and the intercept. Okay. So,
Professor?
Yeah, sure. Ask.
When would the expected value of mu sub I conditional x sub I not be 0? Or are we always doing that?
It's always, almost always not 0. I mean, the thing is, I mean, these lines can be like this line. So you're saying, when is this not 0, right? That's your question.
Underneath it, yeah. Underneath it, you say assume expected value mu sub I
You
conditional
mean
x
this
sub-
one?
Yes.
On the, always. That has to be satisfied always. Like this is
Okay.
always.
Okay, thank you.
This is your assumption. This is like, we can argue whether this is a good assumption or not. We can talk about that later, and I will talk about later, I think.
Okay.
But if there is not, if we don't make that assumption, then we cannot do anything, right? So that's in the heart of what we are doing, right? So
I understand.
so that's the key assumption. So that always holds. If that doesn't hold, then nothing makes sense. And we can talk about later whether this assumption is plausible. It is plausible, and we will talk about that. And when there is no, I mean, clearly you don't have these yellow points, right? And then you simply fit the line with only the white points, right? Let's say you fit a line, and let's say that line is this. What's the expression for that line? That line is the sample line, which is beta 0 head plus beta 1 head times xi, right? And the intercept here will be what?
Beta 0 head.
And the slope will be
beta I head.
Beta 1 head. Sorry guys. This should be beta 1. Archie. Am I clear, guys?
Yep.
So your goal and our goal is to get the best fit. Will we ever know that this line is like a very good approximation of the true line? Do we ever know that these white and yellow lines coincide? We never know that because we don't know beta 0, beta 1.
So we never know the yellow line?
We never know the yellow line simply because you don't know all of the observations. You don't know all of the observations in the population. Otherwise, if you knew all the observations, then you would be able to calculate beta 0, beta 1. Am I clear? This here, guys, I said this is the sample data. If you had population data, then you would have additional data, right? And you would be able to calculate beta 1 hat beta, but then there would not be beta 1 hat, there will be beta 1. There would be beta 0. But you only observe a fraction of the data set. It's this one. So you never know the true betas. But it is proved that beta 0 hat and beta 1 hat are the best possible estimators for beta 0 and beta 1. So before I already told you guys, not today, not yesterday, not the day before, but a while ago, I told you guys, how can you check whether an estimator is good enough?
Consistent,
Is it
unbiased,
consistent,
unbiased,
efficient.
consistent?
That's perfect. So when I say it is shown, I meant that beta 0 hat and beta 1 hat are shown or proved to be unbiased, consistent, and efficient. Estimators for beta 0 and beta 1. Am I clear?
Yep.
And of course, we can reconfirm this. We can show ourselves that they are unbiased, that they are consistent, that they're efficient. But you know, that's not difficult. You can do it. It is in your textbook. You can take a look at it. But it's already shown, right? If you're interested, you can see. Right?
Professor,
Yes.
can you scroll up a little bit? I had a question about the formula you gave us. Like 2 slides.
Oh, sure. This one?
Above this one. Yeah, right here. I just want to be sure that B1 hat is equal to covariance over I think that's variance.
That's variance, that's true.
Okay, so it's sample covariance and sample variance.
Absolutely. So, and then the expanded expression is the sample covariance of xy is this.
So in your numerator, shouldn't the formula also include the probability that x equals xi?
No, that's the sample. That's the sample. It's not the population.
So sample doesn't have the probability part?
No.
Okay, all right.
That's the sample covariance. That's the sample variance.
So solving for sample covariance it's like shorter. It's not as long as solving for population covariance.
For the population covariance, in addition to probabilities, you would have expectation of x and expectation of y. Here we have x bar and y bar.
Thank you.
So there are some differences between sample and population variance, covariance. Right?
Is there any way we could do sample covariance and sample variance on Excel with this data table you gave us?
Yeah, sure. I will. Yeah, sure, guys. So in Excel you can do it. So I will do it for you guys, but maybe not today. But I will definitely do it for you. You can calculate the numerator and the denominator of this expression yourselves once you have the data. So I said, let's say this is your sample data. Can you calculate average? Can you calculate the mean of y? Yeah, you can, because it will be 6 plus 17 plus 2 plus 3 plus whatever is here divided by 5, because you have 5 observations, right? Same thing for x bar. You can calculate this. Now let's talk about measures of feet. There are two measures of feet that we consider. One is r squared. Another one is standard error of the regression. Now I will give you a bunch of formulas, guys. Don't get stress or whatever, because I will explain those later in more details, but we have some expressions, right? You don't have to memorize them. Now let's define r squared. R squared is defined as 1 minus SSR divided by TSS. SSR stands for sum of squared residuals. And then we know what that is, right? That's UI head squared, but you have to sum it up for all I in your sample, changing from 1 to your sample size. And what is TSS? TSS is the total sum of squares. And TSS is defined as of course, you don't have to memorize, but eventually you get it. It's yi minus y4 square, but you sum this up again for overall of your I, which is from 1 to your sample size. So that goes here. And you can calculate this, right? If based on the sample data set, we can calculate this. And then remember that you had I is what? That's yi minus beta 0 head plus beta 1. Yeah.
I'm sorry to interrupt. I just had a quick question. Would TSS be the same thing as a covariance of y?
No, because what do you mean by covariance of y?
Because the formula looks similar to me, so I was getting confused a little bit.
But you meant variance. But you meant variance, right?
Yeah, I'm sorry. Yeah, variance. Yeah, that's what I meant.
But you have to specify, right? That would be exactly as the sample variance, right?
Mm-hmm.
Yes.
Got
Sample. This is the same as sample variance of y.
Got it. Thank you.
Mm-hmm. Okay, guys. Now let me know. So okay, and you get some numbers, right? But r squared is always between 0 and 1. Why is that?
Is it probability?
No. That's because this will always be less than 1. This ratio will always be less than 1. And this will always be positive because of that. Now let's briefly talk about what does it mean if r squared equals 1, r squared equals 0. It means a bad fit. Why is that? Because remember, r squared is 1 minus sum of squared residuals SSR. Okay, let me write this. Summation, sorry, ui head squared, and they have summation of yi minus y bar squared. So if what?
I'm sorry to interrupt. Does it mean it coincides?
Yeah. So if this is 0, then this means that this is 1. If this is 0, because 1 minus 1 will be 0 then.
Makes sense.
But what does it mean that this is 1?
That's 0.
That means that the variation in your dependent variable is completely explained by the residuals, right? So that means that is something you don't really, that means that your model is complete trash, because you have independent variable and the residual, right? And you want that independent variable explains a fraction of the dependent variable, the variation in the dependent variable. But if r squared is 0, that means that this thing is 1, which means that the variation in your dependent variable y, which is measured by the sample variance, is completely explained by the variation in your u hat. Think about this, guys. So there's nothing left to be explained by your independent variable. That means your independent variable does not really play any role in your model, and your model is a trash if that happens, right? So because of that, we say that r squared equals 0 means a bad fit.
Question, Professor.
Sure.
What if that variable was outlier? I mean, there was like a very positive correlation, and then just one variable which we are choosing is just.
That will be very suspicious. Let me talk about that as well. Now let's consider another extreme. Let's say r squared equals 1. This means like a perfect fit. But beware, I would say. This perfect fit might be deceiving, might be hiding something, some problems in your data that could give us r squared very close to 1. We will talk about that problems later in the course. But r squared very close to 1 could be very, how to say that, very suspicious. It's like suspiciously great fit. So if r squared is between like 0 and 1, that's not that's okay. So r squared can be between 0 and 1, and that means that x, your independent variable, explains a fraction of the variation in the dependent variable. Guys, am I clear?
Professor?
Yep.
Yes.
So when r squared is equal to 1 or close to 1, does that mean that the points are like relatively close together?
Yeah, that means that they are like very close to the line.
Yeah, very close to forming a line. And when they're close to zero, it's like they're very spread apart and you can't really draw a line.
Yeah, but the thing is, the reason of having r squared equals 1 could be not because of that, but because of something else, some other issues that you may have in the data. And maybe because of that, you have this high r squared. When I say r squared close to 1, I mean like 0.86, 0.87 over, let's say, 0.95. You know how difficult it is to have r squared like over 0.90. It's really difficult. And if you have like only one independent variable, that's like very suspicious.
Question,
because
Professor.
because one variable definitely would not be enough to explain. One independent variable cannot really explain most of the variation in your dependent variable. And if you have one independent variable and like r squared greater than 0.90, that's really, I would not believe in your model in that case.
Question, Professor.
Sure.
Would the suspicion reason be the population or the sample size is too small?
Sorry, are you asking why do we have r squared close to 1?
No. You stated that r square close to 1 could be very suspicious. The reason would be the reason behind the suspicious reason be that the sample size is too small.
Could be.
Oh, okay.
Yeah, that could be one of the reasons. That's true. But all I wanted to say, we will clearly have more discussion about the measures of fit. One of the measures of fit is r squared. But in today's class, what I just wanted to say is that if you have r squared close to 1, does not always indicate a perfect fit. Like if you have just one independent variable and r squared close to 1, then that model is a bad model, because just one independent variable is not enough to explain most of the variation in the dependent variable. Am I clear? That's all I wanted to say right now. We will have discussion on that later. So am I clear, guys?
Yes.
If you have r squared between 0 and 1, that means that your x, or independent variable, is useful in explaining the variation in your phi. That's all it means. Let me now explain another measure of fit, which is standard error of the model, or standard error of the regression. And it is given by the following expression. That's the square root of 1 over n minus 2 times the sum of squared residuals. N is your sample size. And okay, SER will clearly be always positive because it's a square root, right? It's probably clear, hopefully clear, I mean, that's clear. And SER, let me ask you guys, do you think that high SER is good or bad? Higher SER is good or bad?
Can you define what SER means again?
SER is given by this expression, and you know that it's bad. You had this residual.
Okay.
Not error. Whoever was that, you had this at the residual.
You have higher residual?
That means that the residual explains most of your the variation in most of the variation is dependent variable, guys.
So if this number is higher, what it's a bad thing?
It's a bad thing because higher SCR would be, you would obtain higher SCR if this is bigger. If this is bigger.
And what does that mean if that's bigger?
That means that you have bigger residuals.
Oh, okay, okay. I got it.
Quick question, Professor.
Sure.
Does having a high SER mean we have R square closer to 0?
Very good. Yes, definitely.
Gotcha.
Now let me talk about the assumptions of the ordinary least squares estimation, and that will complete our class. That will complete this chapter. As I said, the next class will be on Friday. It will not be on Shrey, did I answer your question? Because I see
yes,
you have expressed.
yes,
okay.
Professor.
So we will not have class next Wednesday. We will have class next Friday, which is October 9th. I will, in a few minutes, I will just list the assumptions of the OLS that will complete this chapter. The next Friday's class will completely be about R, using R for our purposes, and how to analyze data. And the next week, during the next week, I think I'll start chapter 5, and you get enough review sessions too before the exam, which I think will be by the end of October or the beginning of November. And also what I wanted to say is that again, if you guys have any questions, you can always reach out, right? Now let me list the assumptions of OLS. Also, what I wanted to say is that, guys, so maybe you think that you didn't do well enough, you could do better, so for some reasons you didn't do well. That's okay, because you can, if that's the case, you can completely disregard this exam, because as you know, I'm taking the best of 2 midterms. The best result will count towards the overall grade. So you can improve. But the thing is that you will have to determine why you got lower than you thought you would. There is something you have to think about, and if you have any questions, clearly you can ask me. Now the assumptions. What was the key assumption that I already made?
That u of I equals expected value of u sub I given x sub I equals 0.
This assumption has a name, specifically no endogeneity. Next. I will just list the assumptions, guys, and then we will clearly discuss them. The next assumption is that you have an IID sample. Formally, you write this. What IID means, you know, right? That means independent an identically distributed sample. Not sample, guys, population. So xi, yi are, okay, this is a sample from this is an IID sample from the population, which means that, did I write it down? Our IID, which means that, okay, that means that xi, yi, let me say, when n, you have a sample of n, this is like a sample IID sample of size n from the, sorry, from the population. That is what I want to say. So why identically in what sense? Can you tell me?
I think you said each value in the sample is, I'm not really sure what you said, but something about each value in the sample are being the same.
The population is the same.
Identically in a sense that they are drawn from the same population. Independent in a sense that, let's say, having x1, y1 does not affect having in the sample of x2, y2. So did I write it? It's very bad, right? So it's like, how much time do I have? Oh. It's enough. So guys, okay, let's say we have, I will explain this very quickly. So this is, let's say, n1, 2, let's say this is so on, let's say this is 64. They have x and y. They have x1, y1, x2, y2, and so on, so on, so on, x64 and y64. Okay, those are values, right? Those are values, and having x1, y1 does not determine or affect in any way to having x64, y64. That's what it means. I mean, having the first observation in the sample does not affect in any way to having 64th observation in the sample. Like if you have a population of, let's say, 1,000, of size 1,000, 2, 3, and sorry, 3 and so on, right? 1,000, let's say this is your population, and I want to take a sample, right? You can take, let's say you want to take a sample of, let's say, 100. You can have any sample from this 1,000 observations, guys. Do you see? So, and let's say you picked up a sample of 100 observations, and let's say this the first observation is there. First observation being in my sample should not have any effect of any other observation being in my sample. That's what identically means. Sorry, that's what independently means. And identically means that all of these observations, xi, yi, come from the same population. The third and last assumption for this time is that no large outliers. Why? Because outliers, if you have large outliers, that would bias the results. Why? Because having large outliers, the results, the estimates of beta 0 and beta 1. So I think I'll take, let's say, 10 minutes from the next Friday's class to finish this chapter. I almost finished it, but there's like a few other points to make, and I'll take 10 minutes for the first 10 minutes to finish this chapter. I will assign the homework from chapter 4 or on chapter 4 today, guys. You can start working on it because we did cover most of it, and as I said, the next class is on Friday. I'll see you on Friday. And again, if you have any questions, feel free to reach out. Thank you guys for being here. Have a nice day, because we meet on Friday.
Thank you, Professor.
Thank you, Professor.
Thank you, Professor.
Thanks, guys.
Professor.
Professor, I have a question. So, are you still having the meeting hours on Monday or no? Because
I have to see. I don't know. I have to see if that follows whatever I have to see, and then I will make an announcement on that.
Oh, so the school is closed on Monday.
If the school is closed, then we will not have a class on Monday.
No, I mean the meeting hours, not the class.
There's no school on Monday?
If there's no school on Monday, then we will not have class, guys. I have to check.
Then can we have office hours next Wednesday? Because I need help with some of the empirical.
Sure. Then we will have office hour next Wednesday. Yes.
Professor?
Sure.
Go
Ask.
ahead.
Who is it?
Go ahead, whoever wanted to say something. All right, Professor, can you open the midterm so we could like practice it?
Which midterm?
The midterm we just did. I just checked and still I can't view what I.
If you go,
I cannot open. I cannot reopen because then everybody will be able to do it again. But
oh, I mean like just view it, like not open.
You can view it in results.
Oh really?
On the homepage. Yeah.
Can you check it?
Yeah.
It's in review on the homepage.
I mean, if it's open, I'll probably find it.
It should be open because I think you should be able to see the feedback.
All right. Okay, I'll check it out again.
Sure. If you have any questions, just reach out. I will try to help. So guys, do you have any other questions?
Oh yeah, I see.
No, that's it. Thank you, Professor.
Okay, then I'll see you on Friday, guys.
See you on Friday, Professor. Take care.
Thank you. Have a nice day.